Welcome to Maths with EJD. I've been talking about basic calculus, and the last set of videos have been on integration. So the last time I started with integration by substitution, and I've already done the video on substitution, algebraic substitution. So today I move on to trigonometric substitution. When it comes to trigonometric substitution, right, what is happening is that you replace a set of expressions with a trigonometric you replace x, for instance, like if you are integrating something like x squared minus a squared or things like that, you replace x with a trigonometric expression, which you're going to see here. So I'm going to show you all the triangles that will lead to all these things we do. So the most common substitutions will be making x to be a sine theta. In the case of algebraic substitution, we're substituting a whole expression with another letter, say p equals 5x squared, 5x plus 2 or something like that. But here we're replacing x with a trig expression based on the kind of expression you have. So the very popular ones are x equals a sine theta, x equals a tan theta, and x equals a sec theta. Those are like the three common ones. And that they are for transforming integrals involving, so whenever you have to deal with the square root of a squared minus x squared, of course, a squared gives you the idea of like a perfect square or something like that. You have x, if you have a squared minus x squared, you use a sine theta to replace x, and then you go on. Then anytime you have to integrate anything involving square root of a squared plus x squared, you go for x equals 8 and theta. Then anytime you have to integrate square root of x squared minus a squared, you use x equals a sec theta. Now, if you look at it, it all has a pattern, right? Square root of a squared, the perfect square or whatever, is coming before the x squared. So once you have x squared, something minus x squared, then automatically, you're using a sine theta. Then when you have a squared plus x squared, of course, the x squared can come first, and you have x squared plus a squared. So in that case, you automatically will be going for a tan theta. Then whenever you have x squared minus a squared, then you use a sec theta. Now, this is not something you need to cram, because I mean all of these things have you can see how to arrive at this, and I'm going to show you that very soon. So these substitutions are obtained from the reference right angle triangles for the three basic substitutions, identifying the sides labeled x and a for each substitution. So let's see those triangles that led us to all of these relationships. Now look at this, for instance. If you have a right angle triangle, of course, you have angle 90 here. A is the hypotenuse. You have the angle theta, and the opposite of that angle is x. So you have the hypotenuse and x, and of course, automatically you can get the adjacent to be square root of a squared minus x squared, following Pythagoras theorem. So once you have this, you discover that the combination is pretty easy. You simply have sine theta equals opposite x over hypotenuse a. So in that case, you just discover that x is equal to a sine theta. X equals a sine theta. Now, x equals a sine theta, and then you see that is related to the other side, square root of a squared minus x squared. So you see, so whenever you have square root of a squared minus x squared, you just call your x a sine theta. That's the logic of that. Then you have the second one also, where you have, now you have you have angle theta, right? The opposite remains x, but then now your a is the adjacent, and of course the hypotenuse will be square root of x squared plus a squared, as you have here. So in that case, what happens? You can also, if you combine x and a together, you simply have opposite over adjacent. That's tan theta. Tan theta equals x over a. That again gives you that x is equal to a tan theta. And of course, if you relate that with this, so anywhere you see x here, you put a tan theta. So that's how we arrive at all of these things. So all you just need to draw is a right angle triangle. So once you draw a right angle triangle, then you just keep switching x and a, switch the positions of x and a, and then you can see whatever has the square roots and what the angle that combines the x and a together. That's basically how this goes. So even if you forget, you can easily arrive at it again by just drawing your right angle triangle and seeing which one works for which. Okay, so look at this last one now. So here we have so you can see it's just all about playing with the x and a. Keep switching the x and a. Now the x is the hypotenuse, the angle, you have the angle theta, the adjacent is a, and then of course this would mean this other side is square root of x squared minus a squared. And in this case, what happens if you take adjacent and hypotenuse? It's more like you have cos theta is equal to adjacent a over hypotenuse x. All right. So if that is the case, it means that x cos theta, if you cross multiply, x cos theta is equal to a. So it means that x alone is a over cos theta, and x is equal to a sec theta. You see that? So it means that in this place now, if you see square root of x squared minus x squared, you just replace x with a sec theta. So all these things are logical. So draw a right angle triangle, right? And switch x and a in different positions. And of course, once you have your x and a in place, you can automatically get the third side. And then you can get the angle, the trig ratio combining your a and x. And so from that, you get a substitution for whatever x should be in your expression involving square roots. Okay, so now that we have established all that, let's go and take our first example to evaluate the integral of dx over square root of 9 minus x squared from 0 to 3 over 2. Of course, this is going to be a definite integral. We are going to end up getting a particular value, a number at the end of the day. And of course, whenever you have something minus x squared, like you already know, and if you forget also, you can quickly draw your triangle to get that. So whenever you have something minus x squared, you know the x automatically is going to be 3. I mean, the x is going to be a sine theta. And in this case now, a squared is 9. So automatically a is going to be square root of 9, which is 3. So considering that integral, we make the substitution x equals 3 sine theta, right? And that implies that if you differentiate dx d theta, you get 3 cos theta. You know, you have x equals 3 sine theta. So dx d theta equals 3 cos theta. So in that case, it means dx is equal to 3 cos theta d theta. You know, when you multiply through by d theta, like that. Okay. So once you get that in place, we also, so you're in that case, you also have to transform everything. So you have something for dx, you have something from x for x first of all. You know, you have this to replace x. You now have something for dx. But then whenever you have an interval like this, you also have to do make a replacement for that, just like we did when we were substituting algebraically. You have to do a complete transformation with respect to the new expression you have. So we also have to transform the limits of integration using x equals 3 sine theta. So since x equals 3 sine theta, at x equals 0, which this is, at x equals 0, it means that you put, you know, it means you are going to have 0 here, you know. So at x equals 0, that means you have 0 equals 3 sine theta. So divide through by 3, you get 0 equals sine theta. Take the arc sine of both sides. So it means that you have theta equals arc sine of 0. And arc sine of 0 is 0, you know. So that means at x equals 0, theta is also equal to 0. Then at x equals 3 over 2, which is up here, at x equals 3 over 2, theta is pi over 6. How do we get that? At x equals 3 over 2, it means you have 3 over 2 equals 3 sine theta. All right? So that 3 cancels 3 when you divide through by 3. So then it means theta alone is going to be arc sine of 1 over 2. An arc sine of 1 over 2, of at least in the first quadrant. So, you know, sine 30 degrees gives you 1 over 2. You know, sine 30 gives you half. All right. So that means that the theta that arc sine of 1 over 2 is the same thing as theta 30 degrees. And 30 degrees is pi over 6 because pi is 180. 180 over 6 is 30. So at x equals 3 over 2, theta is pi over 6. All right. And of course, if you're not sure of this, you can always use your calculator, and then maybe in your case, pi over 6, of course, pi here is 3.142, but it's beautiful to work with pi, right? You know, especially when you're dealing with trig like this, so you can get something more accurate, so to speak. So now you have done all your transformation. So this whole expression, it's going to become, so for 0, you still have 0. For 3 over 2, you have pi over 6. For dx, don't forget, you have 3 cos theta d theta here. Then for x, you have 3 sine theta. So that's, and x squared is what is there. So you have 3 sine theta all squared. And then you can begin to tidy these things up. So you have 3 cos theta d theta here. You have 9. Square this. 3 squared, that's 9. Sine theta squared, that's sine squared theta. So, and you move on with that like this. So again, you had 9 minus 9 sine squared theta. So you can factorize 9. So you have 9 into 1 minus sine squared theta. And you have 3 cos theta d theta of the normal. Then again, you have 3 cos theta d theta. Then 1 minus sine squared theta, you won't forget that that is the same thing as cos squared theta, because sine squared theta plus cos squared theta is equal to 1. So it means that 1 minus sine squared theta is the same thing as cos squared theta. So now you have this same, nothing has happened to this, but then you can find the square root of 9 cos squared theta, which is going to simply be 3 cos theta as you have here. All right. So interestingly, 3 cos theta cancels 3 cos theta. And what do you have left? Integral from 0 to pi over 6 of d theta. Interesting. So you have, so if you integrate d theta, like I told you yesterday, in the last video, sorry, like I told you that if you integrate d anything, you get that thing. Integral of d theta then becomes theta, and then you have to evaluate it within the limit 0 to pi over 6, meaning that put pi over 6 first, minus put 0, and then you have pi over 6. And of course, pi over 6 is actually a number. It's a constant because you actually had to integrate it. The integral is a definite integral. And that's why you have pi over 6 at the end of the day. So in radian, right? And if you want to put that in degrees, that is 30 degrees. But I mean, pi over 6 is safer to have. Okay. So can we take another example? Here we are trying to evaluate x squared over 4 plus x squared dx. So if you check this out from all the triangles, you discover that the closest thing to this, what we need to replace x with here is 2 tan theta, 2 tan theta. And if you have 2 tan theta, the x d theta is 2 sec squared theta, because you remember when we differentiated tan theta under integration of trigonometric functions, we discovered that when you integrate tan theta, differentiation of tan theta, you get sec squared theta. So integral differentiation of 2 tan theta is 2 sec squared theta d theta. So dx d theta is 2 sec squared theta. So dx alone is 2 sec squared theta d theta. So that is done. Interestingly, this one is just it's an indefinite integral, so we don't have to go through the stress of changing the intervals. So no need here. So we can keep moving. So here you come back and say, for x squared, you have 2 tan theta squared, and that's all you have up and down. So for dx alone, you have 2 sec squared theta d theta like this. And then if you square this, 2 squared is 4, tan theta squared is tan squared theta. Then down here you have 4, and again, same thing, 4 tan squared theta like that, multiplied by 2 sec squared theta d theta. Okay, so now you have 4 tan squared theta up here. Then here you have 4 plus 4 tan squared theta. So you can factorize 4. So you have 4 into 1 plus tan squared theta times 2 sec squared theta d theta. Again, so you need to understand, once you are dealing with trig, you have to be thinking around all the possibilities. So you remember again that sine squared theta plus cos squared theta is equal to 1. And here we have 1 plus tan squared theta. If you divide through by cos squared theta, for instance, so you divide this by cos squared theta, you divide this by cos squared theta, and you also divide 1 by cos squared theta, which is possible. So sine squared theta over cos squared theta, you already know that's tan squared theta, because sine over cos is tan. Then cos squared theta over cos squared theta is 1. Then 1 over cos squared theta is sec squared theta. So you see sec squared theta is the same thing as 1 plus tan squared theta. So you see this 1 plus tan squared theta now is simply sec squared theta from even this expression alone. So this is more like a proof for that. Okay. So you have 4 tan squared theta up here, and then 1 plus tan squared theta, this becomes sec squared theta. And then that is multiplied by 2 sec squared theta. Interestingly, it's looking good that you can now, let me leave this. So you can now cross that out. So sec squared theta, sorry. Yeah, so you can cross 2 sec squared theta out, and then you have sec squared theta gone here. So 2 remains here. So 2 here is 1, 2 is 2. So this 2 is what comes out here now. And you have tan square theta d theta in there. Now, you have tan square theta d theta. So that doesn't look like something you can also do straight up. So we have to think again. So we remember that though it may be difficult to integrate tan squared theta, but we know that 1 plus tan squared theta equals sec squared theta, right? So that means that tan squared theta is equal to sec squared theta minus 1. That if you transfer this one here. So for some reason, you should know that it is easy to integrate sec squared theta because we already know if you differentiate tan, you get sec squared. All right. So it means it is easier to integrate sec squared theta minus 1 instead of tan squared theta like that. Because we already know that the integral of sec squared theta will automatically give us tan theta, because when you differentiate tan theta, you get sec squared theta. All right. So that's why we do it this way. So instead of having just tan squared theta d theta, you now have 2 into sec squared theta minus 1 d theta. So you can open this up. So you have sec squared theta d theta like you have here, and then 1 times d theta, that's simply d theta. So when you differentiate tan theta, you get sec squared theta. So it means when you integrate sec squared theta d theta, you get tan theta back. You know, this 2 here. Then when you integrate d theta, like I told you, integrate anything, you get that thing. So integral of d theta is theta, and then you have to add your constant. So now you have arrived. So you just multiply things out. You have 2 tan theta minus 2 theta plus c. So this is your final answer for that expression. So 2 tan theta minus 2 theta plus c. So don't forget, I have a comprehensive list of exercise, which I'll put in the last video under integration. So please watch out for that. So many questions for you to handle. So that brings us to the end of integration by trigonometric substitution. So this video continues, so please watch out. If you have not subscribed, make sure you do that and click the notification bell so you can always get notified when I have a new video up. Thanks for listening. See you in the next one.